the 21st of October 2025. Just as Atlas reaches peak solar heating, when the secrets of our third known interstellar visitor should finally be exposed, Earth goes blind. For 6 critical weeks, all telescopes become useless in the sun's blinding glare. This isn't just an astronomer's nightmare. This exact blackout window would be perfect cover for anything wanting to change course unseen. But just before the countdown to Atlas changing its course begins, shockwaves hit the scientific world. The James Webb measured a carbon dioxide to water ratio 8 times higher than any comet ever seen, like finding a cake recipe with 8 cups of sugar for every cup of flour. Mars flybys found persistent asymmetry, and nickel maps revealed chemistry that shouldn't exist. What aren't we seeing while the sky goes dark? And what will decide if this story ends in December with routine comet science or a fundamental rewrite of everything we know? The solar glare is absolute. When Atlas crosses behind the sun from Earth's perspective, every instrument, optical, infrared, radar, hits a wall nearly 1,000,000 miles thick. On October 21, the geometry locks in. New moon, superior conjunction, and the object's closest approach to the sun just 8 days later. For 6 weeks, the sky is off limits. This isn't a technical failure or bureaucratic delay, it's pure physics. The sun's disk swallows the line of sight, like trying to see a candle behind a giant spotlight. Even the most sensitive telescopes, tuned to catch faint signatures from the edge of the solar system, can't pierce this kind of radiance. Not in visible light, not in radio, not even with the most advanced thermal imaging. The blackout is total. The numbers matter here. At conjunction, the separation between Atlas and the sun, as seen from Earth, drops to less than 1 degree. That's less than 2 solar diameters, like trying to see a coin behind 2 bright basketballs. The object's own signal, already weak, drowns in the solar corona, a sea of plasma hotter than 1,000,000 degrees Celsius. The glare zone extends for more than 1,000,000 miles. Any attempt to observe through this is like trying to spot a candle behind a stadium spotlight from the end of a football field. Even radar, which sometimes manages to detect objects near the sun, loses coherence in this soup of charged particles and magnetic chaos, like trying to hear a whisper during a rock concert. Mission planners know the schedule by heart. October 21, blackout begins. October 29, perihelion, maximum solar heating. The moment when a comet's secrets usually spill out in gas and dust. But this time, Earth is blind exactly when the object is most vulnerable, most likely to show its true nature. No direct imaging, no spectra, not even a glimpse of reflected sunlight. For 6 weeks, the only thing coming from Atlas is silence. Any change, gas release, fragmentation, even a course correction would happen out of sight. The timing isn't just inconvenient, it's perfect cover. If something wanted to alter its path without getting caught, this is the window, like a burglar who knows exactly when the security cameras are down. The blackout isn't just an observational gap. It's a test of faith in physics, in models, in the limits of what light can tell us. When the object finally re-emerges in December, every prediction, every theory, every bet made during the blind interval will be tested. Until then, the countdown continues and the sky stays dark. Receipts matter. Before blackout, every major observatory raced to figure out what made Atlas so strange. The James Webb Space Telescope, under emergency request from Dr. Melissa Jang, captured the object on September 18. Its infrared spectrum delivered a shock, carbon dioxide to water vapor 8:1. This isn't a typo. In normal comets, water dominates, like in a recipe where water is the main ingredient. Here, the ratio is flipped and then some, a 6 sigma deviation, like finding a person who's 10 feet tall when the average is 5'7". JWST detected strong carbon dioxide, moderate carbon monoxide, traces of carbonyl sulfide. The isotopic ratios looked solar, but nothing else about the chemistry fit the playbook, like finding a familiar recipe with completely wrong ingredients. Internal NASA chat logs show how close this data came to being embargoed. Jang's team argued that missing the solar heating peak would leave the field in the dark, maybe forever. Meanwhile, Japan's KK Observatory mapped the coma in August and September. Nickel lines blazed bright, iron lines barely registered, like finding lots of gold but almost no iron in a rock. The gas release wasn't random. Gas and dust flowed toward the sun, forming a narrow, asymmetric plume. Reviewers hesitated, worried the nickel anomaly might be a mirage or calibration error. But the reduction pipeline held. No artifacts, no instrument ghosts. The nickel was real, the iron was missing, and the geometry was lopsided. The coma stretched nearly 4,000 miles across in narrowband images, like a cloud the size of a small country. Mass loss rates hit about 330 pounds per second. Water production clocked in at just 90 pounds per second. Another clue that something about this object's chemistry and engine runs outside the norm, like a car that burns more oil than gas. Hubble images from July 2 confirmed what ground-based telescopes suspected. A broad, smooth, teardrop-shaped coma, rare even among solar system comets. No sharp jets, no ragged edges, just steady enveloping glow, like a soft light bulb instead of a spotlight with sharp beams. The nucleus itself stayed hidden, but light curve analysis from pre-discovery images by Rubin Observatory on June 21 let teams estimate size 3 to 4 miles across, spinning slowly, almost imperceptibly. No wild brightness swings, no rapid rotation, just a big, cold, quiet traveler, like a cruise ship sailing calmly, instead of a speedboat bouncing on waves. On October 3, Mars-based equipment got their chance. ESA's Mars Express and Trace Gas Orbiter, directed by Nicholas Thomas's CASSIS team, captured the object as it passed 0.19 astronomical units from Mars. The coma was faint but active, steadily releasing gas toward the Sunday. Images and spectra showed sun-facing activity that persisted until blackout. Internal ESA records describe a tense debate over when to release the data, but transparency won. Public confirmation came October 8. The flow geometry, the chemistry, the light, everything pointed to an object that doesn't follow the usual rules, like a player who plays soccer with their hands but somehow doesn't get penalized. 3 interstellar objects, that's the entire catalog. Out of trillions of rocks and ice balls drifting through the galaxy, only 3 have crossed the sun's front yard while humans were watching. The first, Oumuamua, shot through at a steep angle, never even grazed a planet, like a visitor who runs past without stopping to say hello. Borisov, the second, swept by fast, well above the ecliptic, like a plane flying way too high. Now Atlas arrives on a path that seems almost scripted, just 5 degrees off the solar system's main plane, threading the planetary lanes like it belongs here, like a car merging perfectly into the right lane of a highway. Odds of this alignment, about 1 inch, 20,000. Not impossible, but not the kind of number you see by chance every day. Like winning the lottery, possible, but unlikely. Here's how those odds stack up. Most interstellar objects should arrive at random angles scattered across the sky, like balls thrown from all directions. The ecliptic, the flattened, disc-shaped zone where planets orbit, is a narrow band. Only a small slice of space aligns with it. For an interstellar visitor to glide along this plane, and at such a low inclination, takes more than a cosmic dice roll, like hitting a small target from very far away. This raises eyebrows, but not alarms. At least not yet. Astronomers warn against reading too much into a single case. With only 3 ISOs on record, every new arrival looks like an outlier. Small sample statistics play tricks, like trying to understand a country's weather by visiting only 3 cities. If the next dozen interstellar comets show similar alignments, then the story changes. For now, it's a statistical blip, not a conspiracy. Trajectory isn't just about angle. The path Atlas follows brings it within striking distance of multiple planets. Mars in October, Venus in November, Jupiter next spring. Each close pass offers a chance for gravity to push the orbit, reveal any deviation from prediction, like checkpoints in a race where you can measure if someone's cheating. That's why pre-blackout astrometry matters so much. Every data point, every position recorded by Rubin, Hubble, Mars Express establishes a baseline. When the object reappears after conjunction, even the slightest mismatch, a few arc seconds off, could mean something changed. Maybe a gas jet, maybe a fragment broke off, or as some speculate, something less natural. But before jumping to conclusions, the math demands caution. The solar system is a busy place, and the ecliptic is a natural highway. Even rare events happen given enough time and enough objects. What matters isn't just the rarity, but whether the trajectory stays true. December's reappearance becomes the referee. If the orbit matches every prediction, the unlikely path becomes just another data point in a growing record. If it doesn't match, the search for explanations begins in earnest. Until then, the numbers hold their breath, waiting for the next move. Avi Loeb calls this a solar tug scenario. Imagine Atlas as more than a comet, a probe capable of firing its engines at perihelion, using the sun's gravity to change course. If this is real, the maneuver would happen in perfect darkness, hidden behind the sun, exactly when Earth can't watch, like a magician doing the trick when nobody's looking. The only proof would come after a sudden, measurable deviation in the object's path once it reemerges in December. The test is brutal in its simplicity. Every major observatory, Rubin, Hubble, JWST, and ground arrays, will track the object's position to within 10 milliarc seconds. That's the width of a quarter seen from 1,000 miles away. If Atlas follows its predicted orbit, the story ends with physics as usual. A loud, exotic comet, nothing more. But if the path jumps even by 100 milliarc seconds, equivalent to a 30 foot per second velocity change, comet models can't explain it. Gas release, the usual culprit, is too weak and too slow. Only a sudden, deliberate force could fit the data, like the difference between being pushed by wind versus being pushed by an engine. Rubin Observatory rewrites the odds. Before its full survey cadence, interstellar objects were rare events, one every few years, if that. Now, with nightly sweeps and automated pipelines, the expectation shifts from anecdote to archive. Dozens of interstellar objects per year, not a trickle, a flood, like the difference between getting a letter a month versus getting emails every day. Each new arrival logged with precise timing, color, and motion builds a data set that turns outliers into statistics. The next time a hyperbolic visitor threads the ecliptic, it won't be a lone headline. It'll be one of many checked against a growing catalog. This is the future of interstellar object science. Every orbit, every gas release ratio, every fragment trail gets measured, compared, and stacked. Patterns that once seemed suspicious, like low inclination entries or close planetary passes, become testable, not just debated, like having enough data to prove whether something is actually weird or just looks weird. The same goes for chemistry. 6 sigma carbon dioxide ratios, nickel-rich comets, teardrop-shaped glows. With enough samples, the line between rare and routine sharpens. The discipline moves from case studies to population analysis, like the difference between knowing 3 people and surveying 1,000 people. December's reappearance will test whether its orbit matches predictions or shows unexplained changes. If the trajectory holds, it supports a natural comet. If unusual, any deviation could demand new explanations and urgent follow-up. As surveys like Vera Rubin prepare to find dozens of interstellar visitors each year, the current blackout underlines both our advances and our limits. For now, Atlas remains a case defined by solid evidence, open questions, and the promise of answers just out of sight. Like a puzzle where we have almost all the pieces but still can't see the full picture. The answer is coming. In December, we'll know if we're looking at the strangest comet ever seen or something that will rewrite the science books forever.